when not to use. So I'll be presenting till I finish, then I'll take I'll take questions. These points that will be covered today. In introduction, I'll be giving an introduction about timber bead and how it was adopted in ASME Section 9 and when it was adopted. And I'll be speaking about heat treatment and why sometimes it is not practical or not possible. I'll give a brief introduction about the basic metallurgy of hardenable alloys, which are the concern for when it comes to timber bead, and metallurgy of timber bead and how timber bead can control the mechanical properties of the weld and heat affected zone. Then we'll go to the types of timber beads and how this technique was developed over the years, and timber bead qualifications. In this section, we'll cover all essential variables, and we'll give a brief summary about the timber bead qualification, and we'll go and have a look how timber bead welding is covered in different codes and standards, and different codes and standards have a lot of different things to say about timber bead welding. And I'll just give like what kind of considerations we should take when doing the timber bead for P91 material, and we'll share a case study. So as introduction, timber bead is aimed, or the intent of timber bead is to control the mechanical properties of a weld joint and a heat affected zone without the need for heat treatment. So it provides the same mechanical properties as the heat treatment. So this technique was adopted in 2004 of ASME Section 9, but that doesn't mean that it was not in use long before this date. So we have a record of using timber bead welding since 1980s, especially in nuclear plants where accessibility is a concern. So the first technique was used in 1980s was the half bead repair using SMAW electrode. So how it came to existence? If you look at the difference between single pass and multi-pass, and we noticed that in multi-pass welding, the residual stresses are much less from multi-pass welding than the single pass. This is in part because the welding filler, the small welding filler size we use when we weld a multi-pass joint or weld joint will temper, normalize the weld and the base metal, and also refine the grain size of the heat affected zone. So as you can see here, this is a weld joint welded using a small pillar of 3.25 mm, and the white area is the recrystallized area where this area is affected and tempered by the subsequent weld runs. But here the white area is much less, so tempering and refining is not that effective. In addition to this, the small electrode size will result in a smaller heat affected zone as shown here. So this is how timber bead came to existence. So they said that can we set forth a critical parameters to control the mechanical properties by applying the subsequent run and ensuring that the hardness and toughness are not exceeding the limit or the limits in the basement. So this is where it started, and it started, as I said earlier, by the half-bead approach. So when it comes to PWHT, you know, I always ask this question: what is wrong with PWHT? And we don't tend to look for alternative for PWHT when we are manufacturing or fabricating a new vessel. Yes, we don't do this. So the PWHT or applying PWHT becomes a concern when you don't have time to do it. This is applicable when you are in a shutdown or a turnaround, or sometimes you don't have an accessibility. So time here is the main concern. You give me time, all people in inspection field or in welding field, they know that you give me time, I can give you everything. So here the most critical factor is the factor that governs the repair methodology is time. And we know that PWHT is time consuming. In addition to this, not always practical, and can itself result in a distortion or a reheat cracking. So if there is a way to ensure or to adjust the mechanical properties of the base metal and heat affected zone without the need for PWHT, that would be great. And as we'll see in the upcoming slide, timber bead can do this. So before we go to this, I would like to just give a brief introduction about the metallurgy of hardenable alloys in the welding effect and how welding effect will change the mechanical properties. So welding will subject the base metal to a high temperature that can result of creation the heat affected zone and change the hardness or increase the hardness, and sometimes result in enlargement of the grain size because of the fast cooling after welding. So this heat affected zone is the concern. This is where the highest hardness can result after welding. And this is where we have a coarsened grain area where toughness might be impacted. It is clear in this graph that the coarsened grain area adjacent to the fusion line of the weld because of welding. This, of course, because it goes above the transformation critical temperature, and there is a phase change will occur from ferrite to austenite, and upon cooling, the martensite will form, and upon heating, the grain size will enlarge. So this increase or enlargement in the grain size will affect the toughness, and the fast cooling or formation of martensite can result in high hardness values. As we can see here, this is where the hardness the maximum hardness can occur, just near the fusion line of the weld. So ASME codes address this issue and reduce or restore the mechanical properties by PWHT. So can timber bead do this? And the answer, as we'll see, is yes. This is another photo for the coarsened grain area. It is clear. And this photo is for carbon steel welded using high heat input. So this is the reason to why the grain get coarsened or enlarged near to the weld toe. And this dashed line is for hardness indentation. Okay, so this is the relationship between the peak metal temperature of a weld and correlation to the iron carbide phase diagram. So in this area, okay, in this area, this is where the grain gets coarsened, where you have enlargement in the grain size, of course, because of heating during welding, and this is the fine grain heat affected zone. This is the N critical, where the temperature goes up above the transformation temperature, or this line. This line here is the is referred to as EC1. This is the lower critical temperature, which is around 745 degrees Celsius. So this area is where tempering occurs. So this is where we got the mechanical properties restored. So what we need to do is to make this area similar to the tempered area or subcritical heat affected zone, where the grain size are tempered, the toughness is restored, and hardness is similar to the unaffected base material. So so for
Mr. Malge, can you please unmute yourself?
Okay.
Okay. Sorry for the disturbance. I'll just check on it.
It's okay. It's fine. So for the metallurgical properties,
even Omar can mute everyone.
I don't know who's speaking, but it's okay. As long as you can hear me, it's fine. So coming to the metallurgy of timber bead, as I said, the portion of the heat affected zone that exceeds the lower transformation temperature are subject to formation of non-equilibrium cooled microstructure upon cooling. So when you have a slow cooling, this produces ferrite and carbide, which is fine and okay. And rapid cooling can produce a martensite, which is not usually preferred. And intermediate cooling can produce binite. This binite is generally an acceptable microstructure and result in good mechanical properties. Martensite, however, can be softened, and the toughness of martensite can be restored. So in this chart, we see how rapid cooling end up with a different microstructure. So as I said, the essence of timber bead is to temper the previous weld by applying a new weld rinse. So you need an overlap. What we are doing is we controlling some parameters when applying a weld run over a previous weld. So this new weld run will temper the previous weld and the heat affected zone as well. So mechanical properties will be restored, and hardness will be reduced, toughness will be, within acceptable limits. Types of timber bead. And as I said earlier, the first timber bead type used was half bead weld repair using SMAW. This technique was used by SMAW electrode. The procedure included preheating before grinding the defect or starting the welding, then grinding, then you use small electrode for buttering the weld. Then you grind half of the weld run you applied in the first layer, and apply a second layer using bigger electrode diameter, and these layers are applied as a large, and the remaining layer will be applied using a larger electrode diameter. So after each layer, you will remove the half bead of the existing weld. So the disadvantages of this technique that it is quite difficult to judge the amount of metal being ground away. So this is one of the most critical parameters. So why weld or timber bead welding is not preferred by many owners, because it depends on the competency of the welder. So removing the half of the bead and controlling the overlap may seem easy, but it's quite difficult. So too much or too little reduces the tempering effect of the subsequent by the subsequent layer. Applying the second layer with the staggered bead is difficult to perform if the previous weld pass were ground smooth. So when you do the grinding, it will be ground smooth, and you cannot apply, or it will be difficult to apply the second layer, and requires grinding, of course, which can be time consuming and difficult to control accurately. Preheat is required to excavate by grinding. So before excavation, excavating the defect, you have to do preheat, and create ALARA concern in certain situations, like in nuclear plant. ALARA refers to as low as reasonably achievable. So this is well known to all people dealing with radioactive sources or working in nuclear plant. So this will increase the exposure time to radiation when you are doing this much of grinding and for the weld beads you apply. And in 1986, a new timber bead technique was developed, which is the alternate timber bead repair technique. So it was called alternate because it was an alternative to the well-known half bead technique. So it was recognized by ASME through a code case for P number 1 and 3, 12A, 12B, and 12C under the code case in 432 in 1986 until 1992. So this technique was used extensively between 1986 and 1992 because there is no preheat used in the during the grinding, and there is no grinding of the weld bead, and requires less preheat during welding. So this is the main advantages of this technique. So you can apply it by preheating the repair area to 150, buttering a total of 6 layers. So in each layer, you are increasing the heat input for the first three layers. So you use a higher heat input in the second layer than the first one, and again a higher heat input for the third layer compared to the first and second layer. So this will result in increasing the temperature of the base metal above the lower critical temperature. This is AC1. I can go back to the chart just to show you. This is the temperature I'm talking about, the lower critical temperature. I'll be using this critical temperature in my presentation, and I'll refer to it as AC1 critical temperature. So this will take the base metal temperature above this lower critical temperature, and upon cooling, transformation to martensite and bainite will occur. This will enhance the toughness and reduce a little bit the hardness, but it's limited. It has limited use for P number 4 and P5A material, P11 and P22 material. So the main concern that this technique result in retransformation above AC1. This is a comparison between half bead and alternate repair procedure operation. As we can see, the advantages of alternate procedure over half bead procedure, that okay, here, no geometry limitation, readily automated. Of course, the technique used in this method is automatic GTAW or TIG welding, no preheat, and less likely to produce defects. So it is better than SMAW, and remotely operated, no grinding of the first layer, and less preheat temperature. Another technique was developed, which is the consistent layer timber bead technique using automated GTAW or manual SAW. So the good thing in this technique that it doesn't take the base metal temperature to above the lower critical temperature, which is AC1. So it is something similar to PWHT. It can restore the mechanical properties of the base metal, similar to PWHT. But as we can see here, when depositing the second weld layer, the fusion zone and has height of the weld layer 2 is such that it is always less than the combined weld layer. So this is the weld bead, the weld layer of the weld layer 2 fusion zone, and has height of the weld layer of the weld layer 2 is always less than the combined weld layer. So this is an overlapping. This is nothing but overlapping. So this is how they control the tempering effect and controlling the mechanical properties of the base metal by overlapping using, as I said, GTAW or SMAW. So the advantages of this technique that it avoids transformation above AC1 temperature and produces timber has microstructure similar to what is produced or achieved by PWHT. And then the controlled deposition technique. This is one of the famous techniques that still in use till this day. This can eliminate the coarse grain region within the haze where creep and reheat cracking have presented problems at elevated temperatures. So in this technique, again, you are controlling the heat input and heat input ratio, and you have an overlap percentage between the weld layers of 50% between the weld rings. So the differences between the current requirement and the requirements of 2004 edition. We'll see how the first how it was adopted for the first time in ASME Section 9 in 2004. So this is the famous table for timber bead, which is QW 290.4. This is where the essential variables are listed. And what I want to emphasize here that these variables listed in this table apply in addition to the variables applicable for the processes qualified as given in QW 250. What that means that if you're using SMAW, for example, for timber bead, you have the QW50, the essential variables, supplementary essential variables in QW50. Those variables are also applicable. Okay, so not only this table, and I'll explain why, and I'll show you why this is important. So these essential variables, in addition to the essential variables in QW50, are required and mandatory to be followed. So when impact testing is required, the supplementary essential variables are also applicable for the qualification. So in QW50, you have the supplementary essential variables and the essential variables. And we know that when impact toughness is required, so the supplementary essential variables become essential. So all this is also mandatory. But we need to keep in mind that when variables listed here in this table conflict with or provide stringent limitation than those in 250, the variables listed here shall govern. So like P number, thickness, carbon equivalent, heat input, and heat treatment. Of course, you have heat treatment requirement, but here we're avoiding heat treatment. So this is a confliction. So the thickness, there is a confliction. We'll see this when we discuss all these essential variables. One note I would like to mention here that in 2004, when it was adopted by Section 9, there was two essential variables required, which is the interpass temperature between each layer and the preheat temperature of each layer. So these were essential variables in 2004. These requirements of measuring the interpass temperature and preheat temperature for each pass were deleted in 2017. And when I searched into why, they said it was they were excessive, but they are still the interpass temperature is still an essential variable. When we go to some codes, we'll see this. When we refer to different codes, we'll see that the interpass temperature is required to be controlled. This is the QW 290.4 in 2004. So the main differences are listed here. Diffusible hydrogen was not an essential variable. So diffusible hydrogen here is not an essential variable, as we can see, whereas it has become an essential variable in 2021 edition. So, the other thing is the requirement for measure and interpass, as I said earlier, were deleted. Similar to interpass, the preheat temperature of each layer was also deleted. That doesn't mean, of course, that preheat is not required, but there was an additional requirement to control the preheat of each pass. So this was deleted. Surface bead placement was not an essential variable. Grinding requirement was not an essential variable. So if which means that if the technique was or the WPS qualified for half bead technique, you can use it for full bead technique. So now this is not possible in the current edition. And grinding requirement was not in the table. So this grinding, it's not like it was not essential variable. It was not considered in the table. But there was a note when they shared this or adopted this. The committee of ASME Section 9, the subcommittee was considering imposing surface bead, bead overlap, and grinding as essential variables in the next edition. And they were added in 2006 edition. So we'll discuss all the essential variables of timber bead, and we'll go for fluid backing. So what do we mean by fluid backing? So when you have a water in the backside of the well, you are as a cooling medium, you are during the qualification, how this will affect the WPS qualification. So it's quite interesting that this effect might work fine for hardness, but it's exactly the opposite for toughness. So for hardness, the preheat temperature, for example, will control the hardness and result in better hardness value. So the higher the preheat temperature, the lower the hardness value result in the heat affected zone. But this is not the case in when it comes to toughness. So toughness will be adversely impacted by the preheat temperature. And if you refer to QW50, you will see that the preheat, there is a limit for the maximum preheat or increase in the preheat temperature for the welding method. So the coolant will control the preheat temperature. Like if you have water inside in the backside, the preheat temperature cannot go above the boiling point of the water. So you are controlling the preheat temperature. So this is more difficult when it becomes to hardness. So when you qualify using cooling medium, you can be qualified for welding without cooling medium. It's exactly the opposite in when it comes to toughness. On the road side, when you are qualified by a cooling medium, you cannot do the welding without cooling medium for in the WPS. Another essential variables, this is grinding. So what they mean here by grinding is, it doesn't mean that sometimes you apply the first bead and you need to do grinding or removing some surface flows or minor flows. So that doesn't mean that it's not allowed. But grinding means use or non-use of half bead technique. So if the test coupon qualified using grinding or half bead technique, you cannot use the same WPS for full bead technique. So the thickness, this is an essential variable to hardness, not to toughness, by the way. So the maximum thickness qualified is the thickness of the test coupon, or it is unlimited if the test coupon is greater than 38. So what we can see that when you are welding the a test coupon, if your thickness is usually the maximum thickness you can use for timber bead, but when it becomes to toughness, reduction of the thickness is not allowed. So or there is additional requirement for reducing the thickness to control the toughness. So these variables not working, simultaneously. You cannot control hardness and toughness together. So you need to know why you are doing timber bead. So this is why I would like to go here. This is why you have 3 columns here. The column A, column B, and column C. So what you need to know is what actually you are controlling in your welding. Is it hardness? Is it toughness? Or none of them? So when hardness or when toughness is specified in the original construction code, you have to follow column B. When it's not, and hardness is specified, you can choose column E. When none of them is specified, you can use column C. But in this case, what you need to do, what kind of tests are required when following column C? It is the same requirement as the normal weld, which is QW451, the bend test and the tensile test. But for column B and column A, the required tests are the bend test in addition to the toughness or hardness. So single or multi-pass, this is a change from single electrode to multiple electrode or vice versa. When you change, you need requalification. Surface timber bead, the deletion of surface timber bead or change from surface timber bead that cover the full surface to that only deposited along the toes of the weld. So sometimes the placement of timber bead is placed over the full surface of the weld, or sometimes it is placed near the toes of the weld to temper this area or the heat affected zone in this area. So if you are qualifying using surface timber bead for the full weld, you cannot change it to beads that only deposited along the toes without requalification. In this case, requalification is required. The type of welding, the change from machine or automatic welding to manual or semi-automatic welding requires a qualification. This is applicable to GTAW because automatic GTAW is preferred as compared to the manual welding for a reason I will cover later on in this presentation related to heat input ratio. So when you change from manual welding to automatic welding, you need requalification. And thermal preparation. This thermal preparation is like thermal gouging, or when you need a thermal surface preparation for the weld. When this is specified, this is also requires qualification. I'll cover now the main essential variables that control the timber bead. And this is related to, I'll start with overlap. So as we can see here in this figure, the overlap is between 25 and 75. Any overlap between 25 and 75 is acceptable and requires no qualification. But when it is done improperly, like the figure on the left side, the red zone is untempered zone. So the sequence should be as similar to this: 1, 2, and 3. And 3 is supposed to temper the heat affected zone of welder number 1 and number 2. And this is where skill and experience is required. This is why temper bead is very difficult. You don't need only competent and skilled welder, but you need also experienced welders who have experience in temper bead when using this technique. So for the qualification, when you want to have an overlap greater than 75, so what you should do now? Let's say that I wanna have an overlap of 80%. So now you have to make an overlap of 80% in the test couple, but that will change the minimum overlap. So it will not become within the range of 25 to 75. Now your new overlap value, which is 80, is the maximum, and the minimum is 80. Similarly, when you are using less overlap value, like less than 25, you need to have a new test couple that is matching with the new overlap value. Let's say that it's 20, and your maximum overlap in this case will become 50%. P number. So I'll just go quickly and refer to this table. As you can see here, P number here and group number is only essential variable when toughness is required. For column B, when toughness is required, and it is not required for hardness. So does that mean that when hardness is specified for temper bead, the P number is not a factor? I mean, does that mean that I can, if I qualify P22 material, I can use the same WPS for P11 and carbon half moly and normal carbon steel? The answer is no, simply because, as I said earlier, these variables listed apply in addition to the variables of QW15. So I'm giving this example just to emphasize that although it is not essential variable here, but it is essential variable in the original or basic WPS qualification in QW50. And that's why that doesn't mean that you can use this technique for different P numbers. So another factor, or I'll go back to P number. And when impact testing is required, it is not only the P number that is essential, but also the group number. Group number is also a critical variable when toughness test is specified, as different group might have different chemical composition, and this will change the toughness properties or austenitic transformation temperature. Just I want to make a note here for P numbers that some materials, the P number of some material in 2010 was changed. So when you refer to an old WPS, you might find that the P number is different. And another point here, that where temper bead welding is to be applied only to only one member of a joint, like in case of cladding, like when you have a dissimilar weld joint, like carbon steel to stainless steel, and you apply a battering of 309 on the carbon steel side, and this requires PWHT as per the specification or whatever. So you can use the temper bead for this joint only, and for this part of welding only, for battering 309 filler to the carbon steel, and the subsequent welding will be done normally without temper bead. Carbon equivalent. This is also an essential variable when hardness is specified. So the carbon equivalent, we don't refer to the any normal chemical composition specified in ASME section 2B, for example. No, you need to have an actual composition of all elements specified in the carbon equivalent equation. You have different carbon equivalent formulas. All of them are accepted, but you need the actual composition of this. And sometimes it is difficult. Why? Because when you have like high carbon, high chromium, or high Mn values in the steel, you cannot find a test coupon that has higher carbon equivalent value. So when you increase the base metal, when you have a carbon equivalent for the base metal, the test coupon should have similar or higher carbon equivalent value in order to be qualified for welding this base metal. And again, this is essential variable only for when hardness is specified. As we can see here in this chart, how carbon equivalent can affect the hardness values. So the higher the carbon equivalent, the higher the hardness you will get after welding. And diffusible hydrogen is another concern. So this is also an essential variable for both of them, for toughness as well as hardness. So the increase in diffusible hydrogen will require a requalification. Why increase? And what do we mean by diffusible hydrogen? We have a hydrogen designator in the electrode specification or number. And these numbers are given in table 8 of ASME section 2 part C. And as we can see here, H16 is the average diffusible hydrogen expected in the deposited weld in milliliter per 100 gram deposited weld. This is 16. So the higher the value, the higher the expected hydrogen content in the deposited weld. So increasing the diffusible hydrogen designator requires qualification, whereas reducing doesn't require any qualification. So if the WPS is qualified using H8 hydrogen diffusible designator, you can use H4 without requalification, but you cannot use H16 without qualification. Why diffusible hydrogen is important? Because it is, of course, prevent against the hydrogen induced cracking. So hydrogen-induced cracking, as we know. Can you see my screen now? Hello?
Yes, it is clear. Yes, yes.
Oh, okay. Okay, sorry. Okay, hydrogen-induced cracking can be affected by three factors: the hydrogen threshold and residual stresses and susceptible microstructure. So the diffusible hydrogen in the electrode, any moisture in the atmosphere or base metal contamination or moisture in the electrode coating can increase the hydrogen content and can increase the likelihood or probability of having hydrogen-induced cracking. Also, the residual stresses. So, what I'm trying to say, that timber bead is not the intent of this is not to relieve residual stresses, but to control mechanical properties. So the residual stresses after timber bead are always there. You have residual stresses, yes, less than normal welding, but you have residual stresses and susceptible microstructure. What I mean by susceptible microstructure is the HIC is characterized by being brittle or having little toughness. So the lower the toughness, the higher the chances for hydrogen-induced cracking. And as we can see here in these charts, how temperature on this curve, how temperature can affect the diffusivity of the hydrogen. The higher the temperature, the higher the diffusivity of hydrogen. And this is the temperature and toughness. This is for tempered material, but when the material is untempered, you will not have the same, values. So this might also increase the chances to have hydrogen-induced cracking. Preheat. So as I said, preheat is good for hardness and not good for controlling toughness. So preheat temperature is an essential variable when hardness is specified. That's why it is essential variable for method A, which is hardness. So slower cooling rate after higher preheating temperature result in slower cooling rates. So when you start with higher temperature, the cooling rate will be slower. Why? Because it lowers the thermal conductivity of iron and steel. Okay. So this chart. In this chart, you can see how steel composition and carbon equivalent. What is the preheat temperature required for any carbon equivalent? This is, of course, again, because it is required for when hardness is specified. So the preheat temperature here is can be used using this chart. This is how can we estimate the preheat temperature for a steel material. And these charts can show how the cooling rate will be lower when preheat is used. In this chart, you can see you have a faster cooling when without preheat, but when you preheat the joint, the cooling rate will be faster. or slower when you preheat. So this will impact also the toughness, as we can see here with 260 degrees Celsius, how the toughness is impacted, whereas at 90, at 93, it is a little bit higher, and without PWHT, it is also higher. So there is an adverse impact of preheat on toughness of the basement. The heat input ratio. So this is where I want to cover the point of using automatic GTAW, and what do we mean by heat input ratio? So this term is only related to temper bead. So if in basic welding qualification or essential variable for any method, you won't see this this variable listed there, because it is only related to temper bead. So what we are doing is that we have a heat input ratio between the any weld and the subsequent weld run, and normally it is 1.3 to 1.8 developed and proven for P4 and P5A material to control the hardness and the toughness of the weld. So heat input is not the factor that controls the mechanical properties of the base metal or heat affected zone, sorry, when using temper bead. Rather, it is the heat input ratio. So the concern was that if heat input of the second layer is insufficient, so when you have a heat input of the second layer that is insufficient to temper the base metal, the desired properties cannot be achieved. And if the heat input of the second layer is too high, it can cause a grain coursing, as we saw previously in the photos. So it is necessary to control the minimum and maximum heat input when performing temper bead welding. This is why heat input ratio was developed. So what is the issue of GTAW or as a technique? Okay, in SMAW you have this formula for calculating heat input, which is voltage multiplied by amperage multiplied by 60 over the travel speed. But you cannot use the heat input. You cannot calculate the heat input using the same formula for in GTAW. I mean, or the ratio for this. What you need to have is a power ratio. Why? Because the electrode in SMAW, you're using electrode, and this is getting molten, and there is a direct and deposited as a weld. So there is a direct relationship between the current and the weld deposit. But in the case of GTAW, the electrode is non-consumable, which is tungsten. So the amount of deposited weld can vary over a large range of given current or heat input level. So to address this, a new terminology developed, which is the power ratio. And in the power ratio here, we can see that you have the cross section of the filler wire and the filler wire feed speed. So it depends on the feed rate of the filler wire and the filler wire cross section. So this power ratio is to control the heat input ratio when using GTAW techniques. And of course, the automated is a lot better in controlling the heat input or power ratio than manual technique. And that's the reason why it is preferred. And you have an additional requirement for using manual GTAW for timber bead as specified in section 9. Okay, so timber bead qualification, the material of timber bead qualification should be similar. We should have the same WPS. The product form is not critical. The plate may be used for WPS or pipe. If hardness is specified, then you have a carbon equivalent, and this carbon equivalent might have a problem when selecting a piece for as a test coupon, because you need to take like higher carbon equivalent value. But this can be resolved by changing the group number. So in the case of hardness, the group number is not essential variable. So you can change the group number and select a test coupon with higher carbon equivalent to qualify your WPS. The filler wire is typically should be the same as the composition to the original weld, but sometimes in some studies it is claimed that using a filler wire with lower strength is preferred. This is due to the fact that the absence of typical PWHT might result in higher than expected strength. In weld bead procedure qualification, and I'm talking about I'll talk about the last paragraph, which is how the requirement of timber bead using hardness versus impact testing as the basis can change everything. So here, for example, I'm taking an example as a thickness. In the thickness, we saw that increasing the thickness is okay, but here reducing the thickness for hardness, but here for impact testing, decreasing the thickness below the thickness qualified is not permitted. And I'm referring to this paragraph in 403. The minimum base metal thickness is the thickness of the test copper, or 16 mm, whichever is less. So in some cases also, like in B31.1, you have a safety concern where occasions where impact testing is not specified for timber bead, but where the original weld did not require an impact testing qualification. So there is a note in B31.1 where some material at low temperature might change or reduce the impact toughness properties. And this is the reason where sometimes we need to do the timber bead using impact testing, impact toughness. So sometimes you find that it is specified to be followed, this method, impact toughness, although it is not required by the construction code. But because sometimes the impact toughness at room temperature might decrease, when welding using timber bead, you need to follow the column B or toughness method as a requirement. You need to satisfy all requirements for toughness requirement. So qualification of welders, as I said, the welder is this technique depends mainly on the competency and experience of the welder. And as I explained earlier, how overlap can result in untempered has. Here, I would like to just cover this, that the continuity of qualification in accordance with QW shall be followed when using manual. So note that the 6-month rule for continuity is applied where repair of timber bead are done using manual or semi-automatic GTAW or PAW. So when you are using manual or semi-automatic for GTAW, the 6-month rule applies, and you need to have a demonstration, a proficiency demonstration for all welders using manual or semi-automatic GTAW or PAW. This is the timber bead qualification nomenclature of timber bead welding in ASME Section 9. You can use any groove here shown to qualify your WPS. The timber bead placement or the distance of S, the S distance between the timber bead or the surface timber bead is usually in the range of 2 to 4. So when you change this within 1.5, it is acceptable. So this is the limit for this distance. So it is usually for the surface timber bead placement. We are adding this to temper the subsequent weld, and sometimes it can be removed. The surface timber bead can be removed. This is not removal of surface timber bead is not an essential variable, but it is required in some codes and standard. This distance here is within 1.5, and within 1.5 requires no qualification, but usually it should be between 2 to 4 mm. So these are the factors affecting the repair rates, and as we can see that the welder skill. Why I'm talking about competency of welders, because the majority of failure, 27% of weld failures are attributed to the welder skill or poor man workshop in preparation for the welding. So welder competency here again is very important when it comes to timber bead. Codes and standards, and I will start with section 1. In section 1, there was the only method was recognized by ASM in section 1 was the half bead, but in 2021 they changed and they're accepting both half bead and full bead. And this is, I think, the only code where it specifies an acceptance criteria for hardness, and it is only allowed for P number 1 and P number 3 material. This is, of course, after the PWHT. So it's not like we're having a weld joint that is being welded and we don't want to do PWHT. No, but this is when the PWHT is applied and when repair is required after applying the PWHT and before the hydro test, you want to do this repair, you can apply this technique, either half bead technique or full bead technique. So here, the total depth shall not exceed 10% of the full thickness, and post-weld bake out is required, although H4 diffusible hydrogen designation is mandated. So they're mandating using H4 hydrogen designator, and they're mandating the post-weld bake out to reduce the likelihood of hydrogen-induced cracking. This post-weld heat breakout is non-essential variable in QW 290.4. In section 3, and also the post-weld breakout was required with H4 hydrogen diffusible designation. The construction code gives reference to 290 in ASME section 9. So, and the maximum area of individual repair based on the finished surface shall be 500 inch square, and the repair is permitted for P number 1 and P number 3. Timber bead weld repair was permitted in section 3 under code case N594, but in the code it is the only material are permitted are P number 1 and P number 3. No acceptance criteria specified for maximum hardness in the HAZ. In ASME section 1, only half bead is allowed. The permitted or the material are P number 3 group 1 and P number 1 and P number 3 group 1, 2 and 3. And the permitted welding procedure SMAW, GTAW, GMAW, including FSAW, PAW, and SAW. Although SAW is one of the accepted methods in ASME section 9, but it is only acceptable in ASME section 8 division 1. So they have a preheat requirement for 175. Interpass is an essential variable here, and post-weld breakout is also required. The final timber bead reinforcement shall be removed. It is essential variable here. No reference is given to QW 290 in ASME section 9. So they're accepting this technique, but they are not given any reference to ASME section 9. Or no maximum hardness value specified, and no requirement for impact toughness are specified. In B31.3 and B31.1, they do not address timber bead welding. They provide PWHT exemption by preheat. And in PCC2, it is also it is non-construction code, but provides a method of repair of equipment, and gives the option to use timber bead when repairing carbon steel, pressure components, or pipeline having carbon equivalent greater than 45. No acceptance criteria also for hardness. It gives reference to section 9 when requirement of timber bead is not specified in the construction code. In API 510, this is controlled deposition welding. This is applicable for P number 1, P number 3, and P number 4. The permitted welding are SMAW, GMAW, GTAW. It doesn't specify whether it's manual or automatic. They're accepting full bead and half bead. Diffusible hydrogen is H8. Post-weld breakout is required and can be omitted when using H4 hydrogen designated electrodes. When shielding gas is required, the gas shall exhibit a dew point that is no higher than -50. This is for GTAW. No reference is given to QW 290. Preheat temperature and interpass temperature are required in the qualification. The material used shall be the same of the material specification P number as well as group number. So heat input is an essential variable, not heat input ratio. So what they are doing, that they are controlling the heat input of each layer to be followed as per the WPS qualification. But since they are not given a requirement or reference to QW 290, you cannot ensure that you are controlling the heat input ratio, because they don't give a reference to QW 290 for timber bead welding. For NBIC Part 3, we have 7 methods. 2 through 5 are for timber bead, and the last 2 methods for controlled deposition. In each method, I listed down all the materials permitted and the chemical composition of this material. In weld method number 2, this is when impact testing is specified. So they have an additional requirement for shield gases. So this is the moisture requirement in QW 290.4, which is non-essential or non-essential variable, but they're making it here essential. Full thickness is permitted only for P4 and P5A material. Is not permitted or permitted under certain conditions. When it is tube to header joint is full penetration, and volumetric examination is done after welding. The reason is that they don't want to permit this technique for all weld joints. They specified the using of full penetration or full thickness repair for P4 and P5A. They limited the use of this technique only to tube to header joints. The welding methods are SMAW, GMAW, FSAW, GTAW, and they gives reference to QW 290. This is welding method for P number 1 and P number 3 when impact toughness is not required. So this is mainly for hardness. Post-weld bake out is required. This can be omitted. So in this case, this can be omitted when H4 diffusible hydrogen designation is used and surface bead is removed. So in order to waive this post-weld bake out, we need to use H4 diffusible hydrogen designation, and the surface bead need to be removed. Surface timber bead reinforcement layer shall be applied and removed. So limits specified for minimum preheat and maximum interpass temperature. So as I said earlier, interpass was not an essential variable is not an essential variable in the current edition of ASME Section 9. It was in 2004, but no longer. Here it is also an essential variable. So welding methods, SMAW, FSAW, GTAW process, they give reference to QW 90. P4 is mainly for P4 or method 4 is mainly for P number 4 and P number 5A, and this is without impact toughness. So yes, give reference to 290, and again, full thickness repair is similar to method number 2 is permitted for tube to tube header joint. So post-weld bake out is required and can be omitted when using H4, and the surface bead is removed. Welding method number 5 is for dissimilar welding. These are the P number listed here are the P number for the base metal, and can be when welded to P number 8 or like 300 series stainless steel or any nickel alloy P number 42, 43, and 45. So this is for dissimilar. So when the construction code specify toughness, you should go to method 2 When it doesn't specify toughness, you can go to method 3 or 4. Number 6 is using austenitic for the similar weld or for P91 material. When for P91 material, the 9 chrome 1 moly using controlled deposition. This is limited to butt weld in tubing, 5-inch or less diameter. Stringer bead is are only permitted. Limits specified for minimum preheat and maximum interpass value are specified. Welding method are SMAW or GTAW process, manual or automatic. So for joining P number 15E group 1 to P number 5A, use martensitic filler to be used. And for joining P number 1 to P number 8 or P number 42, austenitic nickel base filler to be used. And P number or welding number method, this is also for 9 chrome material welded to 5A or P8 or P42. This is also limited to tube to tube header where the tubes are 5 inches or less. Again, stringer bead is only permitted. Minimum preheat and maximum interpass temperature are specified. The consideration of P91 material. So in the repair of service exposed P91 material, we know that the strength can be degraded. So in this case, in some studies, they claim that the application of weaker filler metal to more closely match the strength of the material after exposing to the high temperature during service can be used. But this is not the case in NBIC method 6 and method 7. They mandated using matching filler wire, which is B8. So it is critical also that preheat and interpass temperature be lower than the martensitic formation. So this material is martensitic steel. So normally during welding, what you are doing, you preheat, you weld, then you apply post heating, then you cool it down before doing PWHT. Why we cool it down? To ensure that the martensitic is fully transformed before doing PWHT. So this is critical. That's why you need to keep the preheat below martensitic formation temperature, which is around 160. That's why the temperature, the preheat temperature, usually it is 150. P8 consumable are martensitic. They will exhibit lower residual stresses while maintaining comparable creep strength to grade 91. So, and nickel-based welding consumables eliminate the need to simultaneously timber bead both the grade 91 has and the deposited weld. However, in nickel-based welding, carbon migration during welding, as well as carbide formation and coarsening in service are susceptible. Because of and finally, because of the hydrogen contamination expected while using SMAW and GTAW processes, using SMAW, the GTAW process offers the highest chance for success. So here you have less GTAW or hydrogen in GTAW process. The timber bead welding case study, I will share one case study where cracking discovered during routine inspection. This is inside a steam drum. The material was old from 1950s. Difficult to access on the inside surface, and PWHT was not practical. So what they do, that they remove the defect, they prepare the cavity machine, and they install the backing plate, runoff plate. They control the deposition using SMAW weld repair to remove and then remove the backing and plate and runoff plates. They qualified the test coupon. This is the test coupon qualified, and this is the geometry of the weld. In fracture toughness of the fracture toughness was slightly changed. So as we can see here, the toughness of the weld has changed. So it has lower toughness at lower temperature. So what they did is they provided a steam tracing to the weld joint to protect against the brittle fracture. And this is one of the cases where timber bead was successful in as an alternative to PWHT. Again, this technique can be used to as an alternative to PWHT, but if we don't know why we are doing this and what kind of parameters we are controlling, we'll end up with a catastrophic failure. And this is one reason. The second reason is the competency of the welder. So it is because depends on the competency of the welder. Many users or owners do not prefer to go with this repair method. I'll finish here, and thank you for attending, and I'm ready for any question.
Yeah, Omar, there are a lot of questions in the Q&A session.
Yeah.
You are able to access that?
Yes, I'll. I don't know. Shall I start from bottom or?
Either way, it's okay.
Yes. So although allowed by NBIC, grade 91 steel is dangerous steel for any timber bead repair. Repair must be expected in non-hydrogen service.